Assalamualaikum warahmatullahi wabarakatuh. My name is Haikal Ammar bin Hasmizam. We from Group 7 and our group want to present about computerized gear system. First, I will talk about theory. A gear system is used to transmit motion and torque between rotational shafts, and it is commonly applied to reduce speed, increase torque, or change in direction of rotation. In a multi-stage gear train, several gears are combined to produce a large gear ratio with a compact design. The gear ratio is defined as the ratio of input speed to output speed. When the gear ratio increases, the output speed decreases, while the output torque increases. Power in a gear system is the product of torque and angular velocity. However, in practical systems, output power is always lower than input power due to mechanical losses such as friction. Therefore, the performance of the gear system is evaluated using efficiency, which is the ratio of output power to input power.
My name is Muhammad Akmal bin Muhammad Arif. My matrix number is DD240113. So this is the result of the experiment. So first for the table 3.2, we get that the gear ratio for the data, okay, the supposedly the accurate one, which is the gear ratio is 4.333 for all of the gear, the first gear, the second gear, and the third gear. This is because all of the number of teeth for each gear is the same, which is 78. And then we get that our data, the gear ratio for us, for our data, is 4.32 for the first gear, 4.326 for the second gear, and 4.337 for the third gear. And we get that the gear efficiency based on our data is that first gear is 0.995, the second is 0.998, and the last one is 0.999. This shows that um, the gear is actually very efficient, highly efficient to transfer the speed and the torque and the power. But there are minor differences. It's not 100%. It's probably because of the data. Probably because of our mistakes, small mistakes on the reading of the speed. And then next for 3.3, which is the same, but the gear ratio is different for since all of the gear has different number of teeth. The first one has 38, the second one has 78, and then the last one has 118. We can see that the the gear ratio for the first gear is 2.111, second one is 4.323, and then the last one is 6.556. And we get that compared to our data, which is the experimental data, we get that the first one is 2.108, the second one is 4.321, and then the last one is 4.568. And when we compare this to the data and experiment, we get that the gear efficiency is 0.998, 0.997, and 0.998. Okay, basically, it's very close to 100%, same as before. It's the minor difference could probably be because of our mistake in taking the speed data. Since there are minor differences like 3.1, 4.2, there's a bit of minor differences. Okay, so for the calculation, first we need to calculate the theoretical gear ratio. Okay, so for the first set where all the gears have the same number of teeth, we can just divide the second number of teeth divided by the first. So 78 divided by 18, we get a 4.33, and it's the same for all of the gear ratio for all of the gears. And then for set 2, where we have different one, we will get that the gear ratio is 2.111, 4.333, and 6.556, using the same concept. Then for the experimental gear ratio, we will calculate it by dividing the input speed divided by the output speed. For example, the first gear at set 2 at 700 rpm, we will get that 700 rpm divided by 332.2 rpm, we will get that 2.108. And then for the efficiency, we will just basically divide the gear ratio for the theoretical divided by the gear ratio for the experimental. For example, 2.11 divided by 2.108, we will get that the efficiency is 0.998.
So now we move to the observation. So first is gear set 1, same size gear. Use identical 70 tooth gear after the initial 18 tooth until 78 tooth pair. So demonstrate consistent speed transmission in match pair. So second is a gear set 2, which is different size gear. Gear increase in size 38 tooth until 78 tooth until 118 tooth. So show how varying gear ratio affect overall output. So rotational speed drop. So large reduction from gear 0, which is 18 tooth, to gear 1, which is 78 tooth, due to the high gear ratio, which is 18 to 78 is equal to 1 to 4.33. So 4, which is a 1 to 1 ratio. So when two gear have the same number of teeth, such as 78 tooth until 78 tooth, output speed is equal to input speed. So 5 is a progressive or cumulative speed reduction. So in gear set 2, each stage further reduce speed, which is total reduction is equal to product of individual ratio. So 6 is tachometer readings, which is stable and repeatable. So after 10 seconds of stabilization at each input speed, which is 100 until 700 RPM, data was consistent. So 7 is a vibration and gear meshing noise. So increase noticeable above 500 RPM indicates mechanical stress or alignment limit at high speed. So 8 is a direction of rotation alternates. So each external gear mesh reverse rotation direction, such as clockwise to counterclockwise to clockwise back. So 9 is external spur gear trains. So standard gear type use, which is mesh externally and reverse rotation with each stage. So 10 is a computerized control panel. So enable precise stepwise adjustment of input motor speed. So 11 is reflective tachometer or non-contact speed measurement. So ensure accurate interference-free RPM readings without affecting gear motion. So last but not least is output speed, torque and system efficiency. Trade-off observed: lower speed is equal to higher torque. So efficiency affected by friction and gear alignment.
For discussion part, the computerized gear system demonstrates how gear parameters such as gear ratio, speed, torque, and direction of rotation can be analyzed accurately using computer-based control and measurement. By using sensors and software, real-time data on rotational speed and torque will obtain, allowing more precise observation compared to manual methods. Overall, the computerized system improve measurement accuracy, reduce human error, and allow easier data analysis. This proved that computerized gear systems are efficient and reliable for studying gear performance in engineering applications. For the question part, first, why are the experimental results different from theoretical values? The differences between experimental and theoretical values are mainly caused by friction between gear teeth, backlash, misalignment of gears, and energy losses within the system. Sensor accuracy and mechanical will also contribute to these variations. For the next, what are the advantages of using computer software for data collection? Computer software enables automatic data recording, real-time analysis, and clear graphical representation of results. This improves accuracy, saves times, and makes it easier to compare experimental data with theoretical calculations.
So, in conclusion, the experiment shows that gear arrangement directly affect rotational speed, torque, and efficiency. Larger driven gear produce lower speed and higher torque, and a progressive speed reduction was observed in multi-stage gear systems. The experimental result closely matched the theoretical values with high efficiency and minimal loss. The computerized system provides accurate and reliable measurement, making it effective for analyzing gear performance.